In this video, we're going to learn about properties of acids and bases. Acids taste sour. Bases taste bitter. Please do not taste acids or bases unless they're foods. But you may know lemons are acidic and they are quite sour. That's good enough. Acids and bases both will change the color of acid-base indicators. They may have different color changes, but they both have that effect of changing the color of indicators. Acids will react with bases, and bases will react with acids. The product of these reactions will be some type of salt and water. We'll get more into that a little bit later, not in this video. Acids and bases both conduct electrical current. But one difference between them is that acids will react with active metals, releasing hydrogen. This is something you've actually seen before. You've seen single replacement reactions where, say, HCl, maybe two HCl's plus calcium metal, for example, yielding calcium chloride plus hydrogen gas. Bases don't react with active metals to release H2. They will, on the other hand, feel very slippery in aqueous solutions, which is actually one of the reasons why soap will feel slippery, because soap is basic. Also, baking soda is basic, and if you've ever touched a solution of baking soda for whatever reason, you'll notice, dissolve some baking soda in water and feel it, you'll notice it's slippery. Bases and acids are, depending on their strength, they can be quite damaging to you. Obviously, baking soda is edible, so it's not gonna be damaging if you touch it. Now, there are different definitions of acids and bases, and two of them we're going to get into in a later video, but one today in this one. The Arrhenius definition of acids and bases is that acids are just things that will increase the concentration of H plus in a solution. And actually, it's really H3O plus that you get from them, because they'll react with water. The acid will react with water, and you'll get a transfer of an H plus to the water to give us H3O plus and whatever the anion part of the acid was. So we had hydrogen and a nitrate. The hydrogen moves over, and you end up with nitrate left on its own. The Arrhenius definition of bases is that they are things that increase the concentration of hydroxide ions in solution. So an example would be sodium hydroxide in water, and I'm showing this in water because the only way it gets from the solid state to being separate aqueous ions is if you dissolve it in water. But obviously, you get aqueous hydroxide ions from this dissolving, and that makes it an Arrhenius base. So strong acids versus weak acids. Strong acids will completely ionize. They will completely separate. And so that's why we can see here, this reaction, there is a single straight arrow. This means that if we start off with a certain amount of HNO3, every single one of those will separate into H3O plus and NO3 minus. They'll all react. This reaction will go 100% forward. And strong acids include the following. They include the hydrohalic acids, HCl, HBr, and HI, not HF. HF is actually a weak acid. But otherwise, look below fluorine on the periodic table to chlorine, bromine, and iodine. Those three, HCl, HBr, and HI, are all strong acids. Additionally, H2SO4, with which you're probably familiar, HNO3, which you may have heard about, nitric acid, sulfuric acid, nitric acid, and then we have chloric and perchloric acids are also very strong. Chloric you really don't see very often at all. Perchloric occasionally. It is extremely strong as an acid. So weak acids only partially ionize, and they're basically everything that is not listed up here. So any acid, and remember an acid has to have an H coming out in front. So for example, CH4 is not an acid. However, anything else pretty much that has an H that's coming out in front, you should consider as an acid or potentially an acid. So this is H2CO3, known as carbonic acid. It is an acid, but it is weak. It's not one of our 7. And so what we say is that it partially ionizes, which is why we draw equilibrium arrows here. This goes actually only less than 5% forward. The vast majority of carbonic acid in solution is going to be H2CO3, and then only a little bit will break apart and give you HCO3 minus and H3O plus. As for bases, the hydroxides will dissociate because you've got this ionic compound. All hydroxides are strong, but the group 1 and 2 hydroxides are quite soluble, and so with those, you'll be able to actually see a significant strength of basicity. So, this could be NaOH, LiOH, we could have KOH. These are the group 1 hydroxides. There's also calcium hydroxide. There's barium hydroxide. These are all strong bases. Amines are weak bases. So for example, ammonia, NH3, that is a weak base. It can act as a base because, notice, if it reacts with H2O, you'll get NH4+, and if the H plus leaves the water, you end up with hydroxide. So this is, because it's reacting with water, you're getting the increase in hydroxide concentration, not as though there's a dissociation here as happened with the sodium hydroxide, where it's separated into its different ions. I said amines are weak. This is ammonia, but there are lots of other cases that contain nitrogen that are organic molecules like CH3, NH2, and a lot of other cases where there's that nitrogen there that can act as a base. I would say, generally speaking, in this class, if you see a carbon atom and you see a nitrogen, we're probably looking at a base, unless it's positive, unless it's like a CH3, NH3 positive. But that's something else that we'll have to get into when we talk about conjugate acids and bases for a later time. Anyway, that's our quick rundown of the properties of acids and bases, something on their strengths. Let me know if you have any questions or comments in the comment section below. Thank you.